Okay, welcome back everyone. In this second projectile problem example, we're going to be looking at another major situation that you see a lot. And in this one, we call it delta y equals 0. And what's happening is an object leaves from one height and comes back to the same height. So that means that y final and y initial are the same, which leads to delta y is 0. So in this example, a really strong ant throws a pebble from the ground with the speed of 50 meters per second at an angle of 65 degrees above the horizontal. So when we talk about these types of problems, we usually have to make a couple of assumptions. For example, I chose an ant because we can reasonably say that the initial height is basically 0. So that means that the final height is also 0. And if I draw a picture of the situation, so there's the ground, and the pebble is launched with a speed of v initial, so 50 meters per second at an angle of 65 degrees. But the actual path that the projectile is going to take, it'll start tangent to that and then kind of do one of these. Okay, so there's a lot of symmetry in this path. Just as a reminder, in the previous video we talked about a cliff problem, which does not have as much symmetry. It's a little bit easier to figure out, and in this cliff problem that we did a horizontal launch, so that was a little bit easier. The next video, the final example, will be when we launch from a cliff at an angle, and that's the most challenging to deal with, but that's the last video. So in any case, we want to figure out a couple things. First of all, how long is the pebble in the air? What's its maximum height it reaches? What's the horizontal distance it travels? And just for fun, what's the velocity of the pebble the instant before it hits the ground? So to figure out how long it's in the air, we're going to use a little bit of symmetry, but we should always try to write down things that we know. So we know that we're going to have a Vx initial of 50 cosine of 65, which is about 21.1 meters per second, and we have a Vy initial of 50 sine of 65, which is 45.3 meters per second. Alright, so the thing that we can use for part A to find the time of flight is we can use the fact that the time it takes to go up is equal to the time it takes to go down, and because the total time of flight, t total, is t up plus t down, what goes up must come down, and we can say that the total time of flight is twice the time for it to go up. So if we can find that time, we're all set. In a moment, I'll show you another way to arrive at the same answer. So to find the time for the pebble to travel upwards, we think about what's going on at the highest point. Well, if it's at the highest point, that means that it's not going up anymore and it hasn't started falling down. This only happens for a fraction of a second, but at that point, so at the top, what can we say about Vy? Okay, you guessed it. Vy at the top is going to be 0. Alright, and if we start with Vy initial, then this could be a Vy final. So we can use our velocity equation, Vy final equals Vy initial plus gt. Plugging into this, we have 0 at the top is equal to 45.3 meters per second plus negative 9.8 meters per second squared times t up. So it's very important to realize this is t up. Okay, so we do the math for this, we solve this equation, and we get that t up is about 4.62 seconds. So go ahead and pause if you need to convince yourself that this is true. So then, once we have figured up the time for it to go up, we plug it into here, and twice that for the total time is about 9.24 seconds. So this is what we would call the total time of flight, 9.24 seconds. Okay, so you might be asking, all right, is there a second way to do this? And it turns out, yes, there is. Because what is the initial height? Well, the initial height is 0. And what is the final height? Well, the final height is 0. So the change in height for the entire trip, the displacement, if you will, is 0. So delta y, which is equal to Vy initial times time, plus 1/2 gt squared. That's our equation for vertical distance. We can also put in 0 for this. Vy initial is 45.3. We don't know the time, and this is the total time. And we can put in negative 4.9, that's a half of 9.8, and then this is t total squared. Okay, now the neat thing is we get to take this expression and we get to cancel out a factor of t. It looks like we have a quadratic, but really we don't. So we cancel out a factor of t, and what we get is that t total is 45.3 meters per second over, I was being careless, 4.9 meters per second squared. Alright, so go ahead and get your calculators out and pause the video and calculate this, and sure enough, it's 9.24 seconds. Okay, so it doesn't matter whether you find the time for it to go up and then double it, or if you use the delta y is 0. Both get you the same answer, because there's a lot of symmetry here. Okay, so part B, what's the maximum height the pebble reaches? So for this, there's two ways to find this, and I'll just quickly set them up. First, we could find delta y, the displacement, at t up. So Vy initial times t up plus 1/2 g t up squared. So delta y is 45.3 times 4.62, that's the time to go up, minus 4.9, that's 1/2 of negative 9.8, and then 4.62 seconds quantity squared. And when you calculate all of that out, you get a maximum height of about 105 meters. So that's one way to do it. The other way to do it is to use, wait a second, I forgot. Oh yeah, the forgotten equation. So Vy final squared equals Vy initial squared plus 2g is acceleration, delta y. Okay, and again, we're talking about the maximum height, so we're looking at the halfway point, and at the halfway point, Vy is 0. We have 45.3 quantity squared, and that's meters per second, plus 2, negative 9.8, and delta y. And I'll leave it to you to do the math and to see that delta y is also 105 for this. Alright, so moving on. Now we want to find the horizontal range. In other words, we want to find delta x. So delta x is Vx initial times t. So go back and look at the first two, the first example or the other projectile video if you're unsure about this. And this was 21.1 meters per second was Vx initial. And this is t total that we're talking about, because now we want the entire time of flight to find delta x. Okay, and t total is 9.24 seconds, and when you plug that in, you get about 195 meters. Okay, and then finally, let's say we want to find the velocity right before impact. Okay, so v right at impact. Of course, after impact, it's probably going to be 0, but we're talking about right before it hits. And at that point, the velocity vector is tangent, so it kind of down at an angle like this. And it has, so this is v final, vx final, and vy final. And we can find those because we know that vx final is equal to vx initial, or 22.1. Okay, and vy final we can find from our velocity equation. So this is 45.3 plus negative 9.8 times 9.24 seconds. That's t total, by the way. And surprisingly enough, what we get is that vy final is negative 45.3. Negative 45.3. You might have a little rounding error, but basically you get the same number. So again, there's a lot of symmetry. What goes up must come down. And when we start, it had the exact same components. Okay, we had vx initial and vy initial, and at the end we have the exact same thing. So when you do the math, you will find, using Pythagorean theorem, that v final is about almost exactly 50 meters per second, and then if you do the inverse tangent of 45.3 over 22.1 to find the angle, you will get negative 65 degrees because it's below the axis. So hopefully this helps you a little bit with so-called delta y equals 0 problems.